Students, ladies and gentlemen, welcome to this pair distinguished lecture series. My name is Qingyan Chen. I am the director of Poly Academy for Interdisciplinary Research. Today is with my great pleasure to introduce our distinguished speaker, Professor Zhigang from Harvard University. And I'm so happy to see him again. I have a very deep personal relationship with Professor Suo. About 20 years ago, we were in the same research team led by Professor Li Jinghai from the Chinese Academy of Sciences. I learned quite a lot about his work. So we could get reconnect. This is really a great honor for me. So Professor Suo is Alan and Marlene Pocklet Professor of Mechanics and Materials at the Harvard John Paulson School of Engineering and Applied Sciences. He is renowned for his work in mechanical behaviors of materials, covering areas such as solid mechanics, fracture mechanics, soft matter, and soft machines. His research explores how materials deform, fracture, and self-assemble, particularly at very small scales, with applications ranging from microelectronics to energy systems like lithium-ion batteries. What makes Professor Suo's work especially impactful is his ability to bridge fundamental sciences with real-world applications, driving transformative innovations in durable, sustainable, and practical materials. In material sciences, there's often a trade-off between toughness and stiffness. Professor Suo's team has found an innovative way to overcome this limitation. And his team developed a new type of rubber by preserving long polymer chains and introducing a highly entangled network known as a tangimer. The result is a material that is up to 10 times tougher and far more resistant to wear and tear. I just, it's a long list. I don't need to read everything. So I will say that Professor Suo is one of the most influential overseas Chinese scholars. No matter you are in any field, you probably can hear his name loudly, not only in the United States, but also in Asia, Europe, in the entire world. So his contribution has earned his global recognition. He's a member of the U.S. Academy of Engineering and the U.S. Academy of Sciences, and also a foreign member of the Chinese Academy of Sciences. So without further ado, ladies and gentlemen, please join me in welcoming Professor Zhou.
Thank you so much, Professor Chen. All right, so thank you so much for coming and for inviting me to give this lecture. So today's talk, all these words should be familiar to people. Adhesion between soft materials and tissues. I'll explain what it means. Now, but I want to tell you how we got into this business. Some years ago, 2012, we hit upon a really good idea in hindsight. We were working on a class material called hydrogels. So this hydrogel, it's like a tofu, like a jello. It can contain, in our case, 80% water. But our hydrogel is nothing look like tofu. So this material is highly stretchable. So here's a piece of hydrogel. So hydrogel is transparent. You're looking at a black background. So this piece of hydrogel can be stretched 21 times, very stretchable, highly stretchable, and very tough. Tough in mechanical engineering means this. If you cut a crack in this material and you stretch it, this crack becomes big hole, but the crack does not extend. So this is a tough material. So of course, tofu doesn't behave this way, right? So this material has a toughness about this number, about almost 10,000 joule per meter squared. At that point, it was a world record for tough hydrogel. So by comparison, tofu and Jello is a 10, and most gel is about 10. Contact lenses, 100. Cartilage, 1,000. Natural rubber, I'll come to this number. We actually recently improved natural rubber as well. But this is a standard value, 10,000 joule per meter squared. So that material we started. So now let me tell you the mechanism, why it is so tough. So so this polyacrylamide is a common hydrogel made worldwide by many laboratories. So this hydrogel has a polymer network. This is a polymer network. So the polymer network, each polymer strand is coiled like spring. So, and when you stretch this material, it becomes straight. So that's why it's elastic. You can stretch a long distance. In hydrogel, in between polymer, we have water. As I said, water is about 90% in volume or weight. So now when a crack coming to hit a chain, so this chain will be straight and then it break. So when it break, the crack will extend. So the toughness is the energy needed to extend this crack per unit area. It's a joule per meter squared. For polyacrylamide, this common gel, this is actually quite tough gel, 100 joule per meter squared. That's order magnitude. So we also have another material, biomaterial, coming from seaweed. So this material also made of polymer. It's a hydrogel, one polymer chain and another polymer chain. And this polymer chain, these polymer chains are cross-linked by ions, in this case, calcium. So then when crack coming along, it doesn't break any chain. It unzip ionic cross-link and unzip this, unzip that. So then the crack extend. The energy needed, this material is called alginate. The energy needed is about a tofu-like level, 10 joule per meter squared. So you have a sense how these materials behave. So what we did was combine these two materials at molecular level. So now, and this material, this hybrid, achieve the toughness about 10,000 joule per meter squared. So this actually is not, let's see. I don't know how it works. Okay, so, all right. So now, why this material is so tough? It's a combination of two materials. So one crack coming along, before it breaks this polyacrylamide chain, the polyacrylamide chain itself is very strong. It's a carbon chain, like diamond, very strong. So before it breaks this chain, it causes a lot of unzipping of this alginate. How large the volume involved, or the length scale is on the order of millimeters to centimeter. So enormous volume of ionic unzipping. So that's why the combination of this hybrid achieve enormous high toughness. So we said, so there's a one brittle material, another brittle material, you combine them, give you a tough material. So as you can tell, this is a basic principle. You can turn essentially any material to be tough. At that point, this idea for hydrogel was a novel. So once we developed this material, the reviewers, editors were kind enough to publish this paper. but they raise a question. What is this material good for? What is this material good for? So we were searching our soul and our head. We found one use. So this lead to another good publication. So literally, we answer that question. We say, aha, this hydrogel is highly stretchable, but rubber is also highly stretchable. It's also transparent. So these two gentlemen, two postdocs in the group at that time, Korean and Austrian. So in front of them is this transparent material, highly stretchable hydrogel. It's also an ionic conductor. Why? Obvious, because this material contains about 90% water. Water can dissolve salt. Salt is an ionic conductor. So now suddenly you have a stretchable, transparent ionic conductor. So you can publish another good paper about, in order to publish a hydrogel in science, you need to have a good reason. So the good reason is it's ionic conductor. So it leads to many, many devices. Today is, I'm not going to talk about these devices. We actually have two reviews. There's many people followed this up idea, including ourselves, many, many papers over the last 10 some years. So I won't tell all the example, but I want to give you one example that leads to adhesion. You can see why adhesion is so important. All right, so the example is about this technology. It's called technology of artificial muscles. So the technology started with another group, 2000. So the idea is people know about a muscle. Muscle have a complicated biochemistry, but we're not going to, or this paper is not going to mimic the anatomy. Try to reproduce function. The function is once you have an electrical signal coming from brain, the muscle will move, right? Once you think, you can lift your feet. That's the function. So the mimic is the following. So these people just use a ordinary elastomer, a rubber-like material, stretchable material. It's an insulator, soft insulator. And then they put two soft conductor. You apply a voltage. That's your brain. This voltage is your brain. And then the positive charge and the negative charge attract each other. So the thickness of the insulator becomes smaller and area becomes larger. So you move, right? So that's a mimic. Now, so we have been in our group, actually worldwide, many, many groups were looking at this technology around that time. We were looking at this technology. The technology has one issue. We call it the dark side of this technology. So I mentioned that you need to have insulator, soft insulator. That was a beautiful material, transparent elastomer called a VHB. Itself is adhesive tape marketed by 3M. You also need to have a conductor, also need to be soft. So conductor for the technology at the time is a carbon grease, dark, very dirty when you work with this technology. We said, how about I replace this carbon black with our hydrogel? Then the whole device becomes transparent and it's very clean. So that was the idea. That was single idea in that science paper. So we made it happen. It actually very robust. So all we did is the following. We have this elastomer, transparent, VHB, and we have a hydrogel called electrolytic elastomer. In the sense it's ionic conductor, right? Transparent, up and the bottom. And when you apply a voltage, as I said, thickness become smaller, area become larger. Here is an experimental photograph. So when voltage is off, you have a small heart. When voltage is on, the heart become big heart. You have a big heart. The material, the device is wholly transparent. Beautiful material. And you immediately notice for any material scientist, you will ask this question. Here you have a hydrophobic material, hate water, insulator. And then you have a hydrogel, hydrophilic material. Do you really have a strong adhesion? Reviewer actually did not ask that question. And we did not disclose the adhesion was terrible. We didn't mention that. But at that time, adhesion was a solvable problem. Let's solve it in another paper. So the paper was published, no problem. And then this literally, it's this paper lead us to look at adhesion between an elastomer and a hydrogel. That was very focused. So we soon learned the problem actually was not easy to bond to materials. So let show our first papers. So at that time, exactly the same year, there was a Nature paper published by a well-known group, a French group, Libler. And they achieved the interfacial toughness about on the order of single digit, 1 joule per meter squared. Yeah, Professor Meyer said, that's no adhesion. Remember, our material, the toughness itself, same unit, reached 10,000 joule per meter squared. So this paper, we published a paper. We thought we made a dramatic increase. We double, triple this value. We were very happy about this. It was still terrible because the absolute value is very low. It means you have very low adhesion. So the mechanism is this Nature mechanism. It's a mechanism is you have a silica particle, you have a hydrogel and an elastomer, and you use a weak, non-covalent bond to bond them. That was it. There's no specific chemical bond. It was terrible. We literally tried very hard, almost worked on this for more than a year and didn't improve it. So very embarrassing, very embarrassing. So yeah, anyway, we didn't do a good job. So now, and then meanwhile, there's another group published a spectacular paper. The idea was actually very simple. We learned from this idea, Professor Shuanghe Zhao from MIT. He was a former member of my group, but he just did outstanding. People know him. The guy is just crazily good. So the idea is the following. So all you really need is having a strong bond between one material to this hydrogel. In this case, they use a silane interaction. It's a chemical bond. It's a well-known technology in chemistry, not known to my group at that time. And then once you bond this chemical bond with our tough gel, so our tough gel has this plasticity associated ionic unzipping. You get enormous toughness. They bond to many, many materials and bound to the toughness about 1,000 joule per meter squared. 1,000 is not upper bound. The upper bound can be way higher, from 1 to 1,000. People think about 0 to 1, right? For us, 0 is essentially 0. This paper really is 0 to 1 paper. Really is defining paper. Once you see this, so you say, the basic principle for achieve high toughness, to achieve high toughness, really is the same as achieving toughness in a material. You need to have a strong bond and some dissipation mechanism. So once you realize that, you can achieve many things. So now, so after this paper, people realize adhesion really is a solvable problem. What you need to do is find the function. Why do you need adhesion? What new things you can make, right? So we made a demonstration. This is a collaboration between my group and and with David Mooney's group. David Mooney is really a bioengineer. So we said tissue adhesive. His group really know about this. We wouldn't even know it's a real problem. Around that time, David Mooney's group already identified tissue adhesive as a real problem. The available adhesion is about 10 joule per meter squared. We already know you can achieve about 1,000, right? So all we did is using our tough gel and make strong adhesion. So in this case, there is a tissue, there's a heart of a pig, and here's a piece of our tough gel. And I'll tell you the little chemistry about adhesion. So then this tough gel can form a strong adhesion with a tissue. So of course, you can imagine many applications. I'll give you examples shortly why tissue adhesive is so important. So it can stop blood, it can replace suture, etc. But you can see the top gel adhesive easily achieve the adhesion energy about 1,000. When you reach 1,000, it's comparable to tissue itself. Not much point to get any better. All right, so you can have many chemistry to do that. Many materials do that. It's not a problem. The real challenge or real opportunity is to find applications, not adhesive themselves anymore. So now a little bit of chemistry. It will make a general point shortly. So here's a piece of tissue. Here is a piece of our tough gel. So what we did is to use a bridging polymer. It can form a strong bond both with the hydrogel and tissue with a known mechanism. It's called a bioconjugation. It's a condensation reaction. And once you have this bridging polymer, you can form a very strong bond. Once you have a strong bond plus dissipation of gel, of course you get high toughness, not a problem. So, and then we say, aha, we now know what is a basic ingredient. So here is another version of this to illustrate the point. We call it the topological adhesion. It's a new name for adhesion. For soft material, strong competition. So I'll be louder. So for a hydrogel and a tissue also itself is hydrogel. It has its own polymer network. The issue, generic issue is if your gel and your tissue do not have a direct bonding, you don't need to. All you need to do is some secondary thing can form a ring, form a new network to connect these two. So we call it a topological adhesion. It's a through entanglement. That's all you need. So, and I had this idea, I talked to people, but I'm not a chemist, I'm a mechanical engineer. So, but there is a younger mechanical engineer, this guy, he said, Zhigang, stop talking. We have a real system, can do this for you now. So he really invented this thing from just a vague idea I had. My idea really is just this cartoon. But I don't know how to do it. He found a system to do it. He said, here is a polymer, chitosan, coming from a crab, the shell of a crab. Chitosan. It has the following property. He learned, this is a mechanical engineer, learned a little chemistry. He said it's the following. If your pH value is less than 5, this polymer will dissolve in water. But if you reach pH 7 or above, this material will form strong hydrogen bond. So here, how you make this work. You prepare two gel or tissue, one gel and one tissue. He actually did both. So it themselves have pH 7. Then you replace a solution of a chitosan with pH 5. This pH 5, of course, it's a liquid. You can spread this liquid in between. And this liquid start to diffuse, migrate into pH 7. When it gets in, I see pH 7. I want to combine to form hydrogen bond. Then you have this connection, right? So we call it topological adhesion. This paper actually received a lot of attention because this is a natural way to form strong adhesion for many systems now. So then we summarize, we wrote a review article. This review article is very popular now. 2019 with Zhigang as a first author. So we say adhesion is a solvable problem. It has 3 ingredients. You need to take care of 3 ingredients. First, you need to have a chemistry, the chemistry of bonds. You need to have strong bonds. Then the strong bonds don't really need to be bonding 2 materials together. All you need to do is some kind of topology of a connection of 2 materials. Then you have a third piece, mechanics, that allow you to do large deformation, dissipation, plasticity, viscoelasticity, this kind of thing. So you can see chemical engineers by themselves cannot do it. Mechanics by themselves couldn't do it. Mathematician cannot do it. You need to have integration, this academy of PolyU. So interdisciplinary science. So that idea, that's now in hindsight is obvious. You need to have all 3. So adhesion really become solvable problem. The opportunity is to identify function enabled by adhesion. So I will have some examples shortly, but just to nail down this idea of a topological adhesion. I already described this adhesion, the one apology. So I have one network, each circle represents a network. One network bonding directly to another network through a bonding. That's obviously can work. But often it's hard to do. So I also said this through bridging polymer. So this network, 2 black network cannot bond to each other, but they can bond through a third party, a bridging polymer. That can work. That actually is a prevailing technology now. So the third thing is, this third party don't even need to bond with 2 black. Third party just bond with itself. That can work too. So there are many other topologies all you can implement. You can see it's not one topology, it's topologies can induce high, strong adhesion. All right, so here's another illustration. I have a student, Bao Hongchen. He likes to give it a cute name for each technology. He said, this is a molecular staple. The idea is we want to have a stretchable adhesion. So he said, okay, if I have 2 rubber, all I need to do is do a staple. Because a staple, even though staple is a steel, it's not a stretch by itself. But a staple and a staple are far apart. So the material itself can be stretched. So he made a molecular version of this. He used this cyanoacrylate. Cyanoacrylate is a super glue. It's kind of like epoxy, very stiff. But he said, if I make so cyanoacrylate itself is a liquid, come as a liquid, monomers in a, monomers. Monomers in a solvent. Monomers in a solvent. So then you put this liquid into a droplet, spread the droplet on the surface. The monomers, once it sees the water, immediately polymerize to form this glassy staple. So you can make this, nano scale or micro scale, depending on how you spray it. So as a result, you can get a very rapid adhesion, very strong. and highly stretchable. No problem. So this is once you understand the basic ingredient of topology, chemistry, and mechanics, you can turn your imagination to do all kinds of things. So, all right. So here's another mechanical engineer and Professor Yecheng Wang now. So back then he was a student, try to also come to this adhesion bandwagon. So he said, I can make adhesion really fast. Who says adhesion need to have a covalent bonding? Adhesion can be non-covalent as long as it's strong enough. And he learned a little bit of chemistry himself as a mechanical engineer, a physicist, applied physicist. He said some hydrogen bonding can be very strong and very fast because it's non-covalent. So he found one and made instant and tough non-covalent adhesion. So then another postdoc made a photo-detachable adhesion. She said, here's the idea. Strong adhesion, if you make an adhesion patch onto skin, you want to detach, right? Detach. When you want to detach, adhesion cannot be very strong. He said, how about I make a strong adhesion, so there's somebody changed the format. Easy to detach. If I shine a light or warm it up or do whatever, make a very weak adhesion, then I can have a photo detachable adhesion, right? Strong adhesion when it is bonded. If I want to detach, I shine light, detach. So, and she is actually a chemical engineer. She found a particular mechanism to do this. The way she does this, she learned chemistry. So for certain polymer, the ion environment can have a strong crosslink by ion 3. This ion 3 become very weak. If you shine a light, ion 3 become ion 2. So there we go. You have a strong adhesion. When it's ion 3, shine a light, UV light, it detach easily. So the difference is order magnitude difference in adhesion toughness. So it works. During 2018, 2019, 2017, the group just all students are doing adhesion. Crazy chemical engineer, mechanical engineer, biology people. It's just crazy. Everybody is doing this. Now, there's another mechanical engineer himself now. Professor, all these are professors now. Anyway, he said, I have another opportunity. I am going to do, previously, people say, I modify the surface. So for many applications, modify surface is not good enough because you need to do manufacturing the material. The material is not a surface before you make. So you want to make these adhesion link. We use silane coupling for chemists. So into the material, and then you just during the making the material, the monomers form a polymer, and then this silane crosslink link together. He called this a volume modification, not a surface modification. Silane chemistry is a well-known chemistry. So all you need to do is this molecule, silicon, has 4 bonds. So, and then you hydrolyze it, make this active O, and then you condense it to form a covalent bond, become SiO-Si bond. It's a well-known chemistry. So this can work for infinite systems. So he made that happen. This directly linked to this technology. Another student, a chemical engineer, Yao, developed what we call the hydrogel paint. The idea is inspired by normal, we're bio-inspired. actually household inspired. It's called a paint. The idea is the following. If you are a customer in your home, want to paint, right, your home, you don't want to be involved in dangerous chemistry. You want to have something totally non-poisonous, right? But you also want to have a strong adhesion, so paint does not fall out. Okay, so here's the idea. Standard chemical engineering idea is you do all the dangerous, poisonous chemistry in your factory. You synthesize your paint, and then anybody, house husband, housewife, can do at home without any danger of a poison. You can do paint, your brush, dip, cast, spin, spray, you can do whatever. Then you have a strong adhesion. So the idea is the following, very simple. During synthesis, you want to make this active, the silane chemistry, for example, into your polymer chain and make it stable so the paint can stable during shipping and storage. And then you have some way to, another thing to prime the surface. And then all the house husband, housewife will do, just use this polymer, just have the silane bonding. So you divide the label of making the paint and apply the paint into two separate people, two separate locations. So you can do essentially hydrogel paint. Okay, so now the other thing, this actually took us several generations of students make it work. So at that point, so you probably all heard, people want to do 3D printing, right? Oh, there's a printing. Printing is good, especially if you want to make devices. As I mentioned, in the device you need to integrate elastomer and hydrogel, hydrophobic material, hydrophilic material. So you need to do printing, a layer of hydrogel, a layer of elastomer. So this actually is the title of that paper. Print hydrogel and elastomer in arbitrary sequence with strong adhesion. So once you know about the basic secret sauce, you think it can do. It took some engineering, but it works. So at the end, we actually say, okay, suppose you made this basic assumption. Hydrogel adhesion is a solvable problem. The real opportunity is to discover new function enabled by strong adhesion. So this is one of our more ambitious project. We made a stretchable electroluminescence. So essentially, this thing we make into a fiber. This fiber can shine light when you apply electric voltage, and the fiber itself is highly stretchable. So the shine light part is a ceramic particle called zinc sulfide, developed technology for many decades by other people. All we did is embed this particle in a combination of elastomer and hydrogel so that we can apply voltage and still keep it stretchable. This guy can shine light. Okay, so so there are of course other possibilities. In this case, colleague Ryan Haywood do ionic transistor. If you have two ionic conductors of a different type, positive ions and a negative ion, so they become ionic semiconductor. If you have a p-type and n-type together, form an interface, boom, you have ionic transistor. You can make many, many ionic devices to get inspiration from electronic devices. So that was clearly an idea. Now let's come back to the function again, tissue and gel. So at this point, so this is a later stage. So we ask, and other people, other groups ask the same question. Assuming adhesion problem is solvable, what can you do? The obvious thing is during surgery. There is a classical way of doing surgery. Oh, surgery, this must come from Harvard. So dysfunctional. This suture. Suture is classical engineering, bioengineering. So suture takes a lot of time, takes a lot of skill. So how about you replace suture? For many decades, doctors have this dream by adhesion, so that anybody can do this easily and fast. So now we immediately find an issue when we talk about the surgeon. The hydrogels are too soft. The hydrogels themselves are too soft. It cannot hold the tissue together. So then the new technology, how about you embed in the hydrogel a mesh? All you need to do have a surgical mesh has been widely used. Previously, the mesh is only put on the surface. It cannot hold tissue together. But if you have hydrogel, make a glue, then you can, of course, hold everything together. So we made this work. This is obviously a workable thing. So then we got even more ambitious. So I won't talk about it. Got more ambitious to do a real surgery. This is an organ transplantation. This is a paper really do organ transplantation. You can see why this is important. So this is a thing, in organ transplantation, you need to connect two main blood vessels. So this, in surgery, it's called anastomosis. Just connect two tubes. All right, so before you connect two tubes, you need to shut the blood off, right? And then you use a suture to connect them. And then open the blood vessel. So if you transport a plant like a liver, you need to connect 3 tubes. So even the best surgeon requires about 45 minutes. This record has not been improved for many, many decades, just 45 minutes. So during 45 minutes, the patient blood will be shut off. Very dangerous. Leads a lot of complications, even for the best circumstance. So it's an obvious dream. People surgery many, many decades. Oh, what we should do is doing adhesion. So we made this happen in this demonstration. We really use a pig, 2 pigs. One pig served as a donor, the other pig as a recipient. So we use adhesive, there's a connection, and the pig actually survived a month. The pig eventually died for some other diseases. So this just demonstration it's possible. So yeah, I should. How much time do I have? Oh, 5 more minutes. All right, 5 more minutes. So I have another major section, but let me just introduce a problem. Problem is a real problem, real engineering problem for more than a century problem. Professor Mai will be very familiar with this problem of fatigue. Sorry, the joke is not intended. It's a fatigue of a material. We don't have any cure for human fatigue. It's just a fatigue of material. So this fatigue of material is the following. You have a piece of material, could be metal, could be ceramic, could be hydrogel. You cut a crack in the material and you do cyclic loading. So the crack just grows cycle by cycle. So this is called fatigue crack growth. In Professor Mai's book and papers will describe in detail. But I'll challenge you, not only his book, everybody's book. People can characterize fatigue, but people have very little idea to create a new material to have high fatigue resistance. So early on, we tried our own material, this beautiful material, a composite. Remember its toughness, this value, toughness, is 10,000 joule per meter squared. But if we do cyclic loading, this is a growth, crack growth per cycle, the number reduced to 50. The crack's still growing. So from 10,000 to 50, this material is a crap, right? Under fatigue loading. So, and we learned that this is generic, not only our material, even natural rubber suffers this fatigue problem. Also, number is about 50. So we actually recently made great progress I don't have time to talk about this detail, but let's just come to the immediate punchline. We made some application as well. So we enhance fatigue threshold also to 1,000. Also 2,000, from 50 to 1,000. By this mechanism, I'll skip this part. So the basic message is simple. The adhesion really is no longer a problem. In principle, is solvable. Under monotonic loading, just keep loading up, or under cyclic loading, it's a solvable problem. The real challenge or opportunity is function. Discover new function or imagine new problem or new opportunity to solve. That's a new opportunity. So I'll skip. So we actually make a tire material, fatigue resistant, enhanced by order of magnitude. So I will skip these. So my student will be really upset with me. So please, So here is the slides of the talk. Yeah, I didn't do justice to many papers. Even for the best papers, I only have 1 or 2 slides. But the message really is simple. Adhesion is a solvable problem. It's solved through chemistry, topology, and mechanics. The real opportunity is a function through integrating these several materials. Thank you very much.
Very much for a very enlightening talk.
Thank you.
I have known Zhigang for many, many years. I suppose from the time when he first went to the US, and I was at the University of Michigan at that time. So dates back a long, long time ago. And certainly adhesion is a very important property in materials. All I note about is structural adhesives. So we can do chemistry, we can do topology optimization to improve adhesion, but mainly in solid substrates. So the difference here is that I'm very delighted to listen to all the applications, well, from the basic to the applications, covering a wide range of functions of adhesion of soft material to soft material. So that is really eye-opening for me. So what I would like to do now is to open to the floor for discussions. If you have questions, will you say your name first? And then to ask the question to Professor Shaw.
Yeah, Zhigang from Poly ABCT, material scientist. So I've been following you, as I said, for following your work 30 years ago, and very happy to learn your recent progress on soft adhesion and toughness, etc. My question is something that I learned 30 years ago, still between the metal and the elastomer. So you mentioned you need the chemistry, topography, and the mechanics to address all these issues for the soft. How about the analogy to the metal elastomer case? And I've been working on soft electronics, and therefore that's also an issue that you've been working with, and Professor Mac might been working with for many years. What was the strategy moving forward? Because there are still very difficult mechanics in between these two materials, right?
So if you are referring to specifically about adhesion.
At the interface, let's put it this way.
Yeah, adhesion between polymer and hard materials. I skip a section about specific about that. Once we understand adhesion better, we find we can also improve adhesion between soft and hard material. It's the same strategy. You need to have a strong bond, and you need to have a dissipation mechanism.
Yeah.
So dissipation mechanism, I also mentioned fatigue. I really didn't do a good job. My student would be very upset with me. Didn't even tell the story. All right. So we find we can enhance fatigue resistance also doing cyclic loading between hard and soft material by orders of magnitude as well.
Okay, I'll probably talk to you during lunchtime. I'm sorry, I need to go for another stuff, and then I'll come back later.
Thank you.
I'll discuss with you later. Thank you very much.
Right.
Thank you.
Thank you.
Okay, all right.
Professor, so
Can you
it's
give
very
the names first?
I'm Liu Dongsheng, and I just moved from Tsinghua to PolyU last year. And so we work on the DNA hydrogels and do a lot of quite mechanical studies of the softer matters. So my question, I'm sorry that time is so limited, so you have not sufficient time to go further about the mechanism, about the vertical of the materials. And when you're talking about the constant loading or the cycling loading, the mechanisms, do they do the same strategy or the quite a similar things, or you can just solve the problem both at just in one materials?
Thank you. Very important question. So material fracture, crack grows under monotonic loading. Or under cyclic loading, crack grows slowly. These are two distinct mechanisms. The solutions are actually very different. We can realize solutions in the same material, but require different ingredients, put in different ingredients. Specifically, as I showed, there's just a resist crack under monotonic loading. All you need to do is a dissipation mechanisms. But that mechanism is not by itself is insufficient to resist fatigue crack growth. The reason is very simple. So because you do first loading, essentially you consume this dissipation mechanism. Subsequent loading, it doesn't do very much for you anymore, right? So, and we learned this in painful ways. In several years, we were very depressed. Just imagine, under tremendous pressure, you just publish a paper in Nature. The material later found out to be fatigue prone. Very, very embarrassing. So under tremendous pressure, we tried many things. Eventually, just a student to try many materials because we initially didn't know what will make material resist fatigue crack growth. It wasn't clear to us. So until one day, find one material really has much more higher fatigue resistance. The threshold achieved multiple hundred joules per meter squared. So for months, we didn't know why this material is better than other material. Then find reason, just searching darkness. Eventually, we find out the reason for that material to be so fatigue resistant is the polymer chains in that material is extraordinarily long. Polymer chain is a carbon bond. It doesn't suffer fatigue by itself, right? This chain. So then that's the principle. Once you recognize this principle, you find, oh, in the literature, people actually talk about this many, many years ago. So there is for people know polymer mechanics, it's called a Lake-Thomas model, published in 1967. 67, outstanding paper. Then we ask the question, so this is a question I'm supposed to talk about. Thank you for that question. So there is a punchline. Then we ask the question, why people in so many years ago learn that you need to have a polymer long chains to resist fatigue crack? Why not people make every material with very long polymer chains? Then we will not hear about a fatigue problem anymore. Why is that? And we actually found answer. The found answer is really, making long chains itself is very difficult. Not making itself, just if you have a long chain material, the blending, mixing become really, really hard. As one example, people harvest natural rubber with very long chain. Nature produces beautiful natural rubber. But when engineers make it into a tire, they cut chains into short pieces just because they can blend them. Just a sad story. Every time you drive your car, think about this sad story. The car could be much better. So we actually published several papers in recently, in the last section. We really enhance fatigue resistance after this understanding. So to summarize, answer your question, we now understand how to resist crack growth into static loading and cycle loading, different strategies, but it really requires you to fabricate material, design material beforehand. Principles are clear now.
Okay.
Thank you.
Yeah, thank you. Any other questions from? Oh, yes, please.
So Du Huifeng from mechanical engineering. So thank you for the insightful talk. So I just have one question about the limitation or bottleneck of the clinical adoption of all the hydrogel related technology. So for example, like the hydrogel adhesive. So I heard Professor Xuanhe Zhao trying to sell this technology many times at MIT, right? So he was talking like a suture. It requires a highly trained surgeon to perform it. But their hydrogel adhesive, basically a PhD student can do it. If that is so convenient and powerful, then why, in every hospitals around the world are using the hydrogel adhesive, but they're still sticking to the sutures? Is it because of maybe the toxicity of the acrylamide-related hydrogels, or because of the resistance or reluctance of the adopting new technology? So maybe you can comment on that.
Yeah, well, my comment will be superficial. I'm not a surgeon. I work with a surgeon. Surgeons, of course, know the problem. For example, if you do the transplant, you cut patients' blood transmission off for 45 minutes. That's very painful. There's a strong motivation to accelerate that process, right? So this wish to do that has been over many decades. So the need clearly is there. However, for example, there are also competing technology. So I didn't spend enough time about this liver transplant. The surgeon was a really famous doctor, very famous doctor. He has developed technologies over decades. So he has a way to kind of do improvement not as good as, not as fast as adhesion, but kind of work as well. So hydrogel technology also need to compete with all these other technologies to get clinical approval. So the intrinsic material problems, they are problems, but as far as I can tell, each one is a solvable problem. So, so you're chemical engineers, so you know material science. So if you try to put your finger on all the novel material technology, could be aerospace, could be civil engineering, any critical application materials require decades between the invention of material to widespread use of that material. It's not special. So our strong, tough adhesion technology, it's only about 1 decade. It's a very young science.
Yeah.
He has time.
Yeah.
He is young. He has time.
So you're still like think the technology is very promising in the future, like for clinical adoption.
Yeah. It's a very promising.
Yeah, I think that's also the amazing aspect of the soft matter physics. It bridges the chemistry and the mechanics together. Right? Yeah.
Are there any other questions from this side? No? Yeah. Okay, Zhongqing.
Su Zhongqing from Mechanical Engineering. Professor, thank you very much for your very inspiring talk. Much appreciated. So I have 2 questions regarding the application. So understand the soft material adhesion should be a very critical issue in many applications like the surgical device, soft surgical device, wearable and biomedical application. So from the application perspective, so if we consider the very complex biochemical environment and also the dynamic deformation of the living tissue, for example, when people moving. So what do you think is the most serious obstacle to achieving the long-term stable coupling between the soft material or soft devices and the living tissue in the in vivo scenarios?
Thank you very much. Yeah, this is a very important question. Through doing this, as I try to emphasize, I'm a mechanician. I like to think about mechanisms, molecules, but people in application surgery, the mechanism itself is not interesting to them. They have a specific problem. I really, through this interactions with clinicians, have a really new appreciation for their challenge. So I can give you a few examples of people are dealing with a problem. One is the speed, the instant adhesion, right? If you try to stop blood, right, you need to be very fast in a wet environment. People have, Shuanghe has a solution, other people have other solutions, can achieve adhesion in wet environment rapidly. That's one example. So once you identify, once you can articulate a difficulty, people find a solution. So another thing we also heard from clinician, even for our, there's a tissue transplant example, the adhesion need to be bioabsorbable. So after some time, that adhesive, after tissue grows, that adhesive should disappear. That you can implement. We actually have several line of research to develop a bioabsorbable adhesive, strong first, but then as the tissue heal, the adhesive disappear. So all these are solvable problems. So what I think the new opportunity really is from a functional side to pose the challenge, focus on that particular either medical issue or technological issue and make that work. Adhesion problem is a solvable problem. It's a solvable problem.
Yeah. A follow-up question that is also related. So that's basically, so when you're achieving a strong adhesion between soft material and the living tissue, That is the first step. And then you need to have the follow-up, for example, like some medical diagnosis or medical treatment. For example, in our group, what we are doing is when we couple the software device with the tissue, and then we need to send ultrasound signal, for example. And some people may generate some electrical stimulus or actuators, software devices. So here, one very challenging issue is the coupling issue, like the acoustic coupling, mechanical coupling, because that is soft to soft. When you send the signal, you have the signal transmission, you have the electrical stimulation transport. So this is some issue. So what factor you think somehow we can do something, try to improve the mechanical, acoustic, or chemical coupling between the soft devices and the living tissue?
Yeah, very, very good question. Very good. So I myself haven't really got so involved in this particular challenge, but I have a colleague, very well-known colleague, young guy, Jia Liu. I don't know if you've heard his name. He really insert brain implant into brain and keep recording brain signal over months, half a year. So the issue there, the traditional issue there is when brain sees a foreign object, it grow other tissues so that other tissue will separate the neuron from your actual the electrode. So you stop recording the signal. So but through a combination of being soft or flexible, he can actually stop or slow down the growth of protective tissues. So these are that is a particular situation. The challenge you mentioned is very explicit, and he seemed to make it work.
Mm-hmm.
Yeah, his company just raised lots of money recently.
Yeah. Okay.
Yeah.
Okay.
You know him, Jia Liu from
Jia.
Harvard. He has a company, has multiple companies.
Oh, sure. Okay. Sure. Thank you.
Yeah. The issue is real.
Okay.
Thank you.
All right. Today we have quite a large number of people attending the seminar online, and we have a few questions.
Yeah.
Maybe you can answer them, but two are in Chinese, which I'm not pretty certain I can translate correctly. Two are in English. So I'll do the English one first. And this person was saying that I would like to ask about the bioresistance of hydrogels, how they can achieve actuation. I think you mentioned that already, sensing and signal transduction and how they are powered. I thought you have already covered this, right? So maybe you don't want to supplement any more to this question?
So I didn't do it explain. We actually did a lot of work on this. So the transduction, of course, there's temperature coupling or pressure coupling, or in your case, ultrasound. So these are transduction, and there's also electrical coupling. So people are ionic device, and computer are electronic device. So ultimately, you have an electron-ion coupling through an interface. We spend a lot of time look at these couplings.
Okay.
Yeah.
So the second question is really to talk about when you have so many data, and how effectively do you process them? And can you perform reproducible analysis?
Okay.
So you have so many data. What do you do? How to process them?
So in my group, we typically don't have a lot of data because doing each experiment, for example, fatigue experiment, we make a sample, and each fatigue just one experiment take weeks, sometimes even more than a week. So but in other So we actually specifically design experiment so that we can, in principle, generate a lot of data, essentially test many materials, fatigue test, thousands of sample test in parallel. We do that, we generate data, then we work with a statistician, or today it's called AI engineers. There's a new name for them. So there are strategies. Essentially, I was amazed. I asked them, how can you guys, using a program that trained by recognizing dogs and cats, to analyze the materials data? They're all, it's all the same mathematically. So we actually wrote a couple of papers like this, how to use cat-dog program to analyze materials data.
Two other questions
in
Chinese, but I think I can translate the first one.
Yeah.
It says that soft materials and tissue, when you bond them together, how is the layer of the water would affect the adhesion?
Oh, thank you very much. So hydrogel itself has a lot of water. The tissue itself has a lot of water, 70, 90% water, right? All you need to do, you need to achieve bonding between polymers. So if you don't have direct bonding between polymers, then you have an issue.
Okay, the last question may be, sorry, I can translate this one.
Yeah, let me read this in Chinese.
Okay.
响应生理环境 pH 温度活性氧的智能软粘合剂实现可控脱粘的设计思路。Okay, let me try to translate to English. So presumably you have a responsive system, because hydrogel can respond to many environmental signals, such as pH, sound, electrical, temperature. So if you want to have a responsive system, signal may come from the tissue. How can you transduce these signal to your hydrogel device or even to your computer? So there are actually many, many designs. So this is in the last page of my, so in one page of my talk, I give 2 review articles from my own group. We wrote 2 reviews about these kind of things. It's called ionotronics, the interaction between ionic circuit, people, tissues, and electronic circuit in computer, in devices. So we wrote 2 reviews in Materials Review, Nature Reviews Materials. Take a look at these. These are not just our own work. Of the work really in last decade, just people just made a tremendous progress. Again, so for people who have companies think there are problems, there are actually a lot of solutions as well. The real difficulty, I think, is translation between solutions to real problems.
Thank you very much. I actually have some questions, but I don't think we have time, so I can talk to you about that, but they're more on mechanics issues. And I draw an analogy that your topology techniques is akin to what we do with interface engineering, right? I mean, take a simple case of 2 polymers by interdiffusion on molecular chains. We can actually design the interface toughness. Now, I think the toughness you mentioned about here is about maximum 10,000 joule per meter square. Is it right? That's the maximum you achieve.
No, that is at that time. But since then, even ourselves break that record. Right.
So that's good, but okay, because I think at this point in time, we should thank Professor Zhigang again for his very enlightening talk and open up new areas, perhaps for many of us sitting here. So thank you very much.
to express our appreciation to your wonderful talk. We make a special souvenir for you with your name and the lecture title together. Okay, well, thank you again, Professor Zhou. Also want to thank everyone here today for your participation. And also, especially for those who ask questions, make this very meaningful. Now this lecture is adjourned. Thank you very much.